All right, so last class we were talking about gas laws, and so today we're going to pick up with Avogadro's law. So this is the same Avogadro you learned about with moles. So when you said 1 mole was 6.022 times 10 to the 23rd particles, that Avogadro is the same one who came up with this Avogadro's law. So of course he loves his moles, and so this law is all about the moles. Now something weird is that we use N to represent moles. So N officially means the number of moles. And I know that's a little crazy, but remember we have M used for so many other things that we didn't want just one more M in there. So again, N is our number of moles. So Avogadro's law says that the more moles we have, the greater the volume. So I have that picture of that little girl blowing up her balloon. And the idea is the more stuff she puts in, the more moles of gas she puts in, the bigger the balloon's going to be. And if she lets some of that air out, she lets some of that stuff out, it's going to get smaller. So this is directly proportional. So as the number of moles go up, so does the volume. So you put more stuff inside, it's going to get bigger. Likewise, you let some out, it's going to get smaller. And the stuff we're talking about here are the number of moles of gas. So down here we have our equation, V divided by N equals a constant. So if you imagine that constant to be any number, for example, the number 5, and you increase the volume, the only way to maintain that number the way it is to also increase N. Likewise, if you were to decrease the volume, the only way you could maintain the constant will be to decrease the number of moles. So again, this is going to be directly proportional. So if the number of moles goes up, the volume needs to go up as well. If the number of moles goes down, the volume needs to go down. All right, so the next relationship we're going to look at is temperature and pressure. So you know what would happen if you threw an aerosol can in the fire. So you chuck that into a fire and boom, it's going to explode. And the reason it's going to explode is because as the temperature goes up, so does the pressure in that can. And if we can't relieve that pressure, it's going to blow. So this is a direct relationship. And we could also say that if the temperature were to go down, the pressure would also go down. So again, that is a direct relationship. When one goes up, so does the other. When one goes down, so does the other. All right, so again, pressure and temperature are directly related, and we call that directly proportional. When temperature goes up, pressure goes up. When temperature goes down, pressure goes down. And that should make a lot of sense based on what you could imagine if somebody were to chuck that can into a fire. All right, so back to this slide. We started talking about it last time, and we talked about how there's all these laws, Charles, Boyle's, combined gas, Avogadro, Gay-Lussac's, and in your 102, they may have asked you to memorize all of those laws, but there's two problems with that. One is that that's a lot to memorize, but second is when you're looking at a problem, you've got to figure out which one of those laws to use, and that's a lot to deal with when you're already stressed out about an exam. So the equation that I want you to know is this one right over here, and that is PV over NT equals PV over NT. And I'm going to show you how to use that in just a moment. The other one that I need you to know is the ideal gas law, this one right over here. Now it's true, you can get PV over NT equals PV over NT from the ideal gas law, and I'm going to show you how to do this, but I'm going to tell you, use that as a last resort. You're on an exam, you can't think of that PV over NT equals PV over NT, use the ideal gas law to figure it out. But I think this is only two equations, and so I think it is easier just to learn these two equations, but of course it's up to you. Let's take a look at how to find that second equation from the ideal gas law. So the first thing I'm going to do is solve for R. So I'm going to say PV over NT equals R. So all I've done is divide both sides by NT. Now I'm going to write this again, and I'm going to say R equals PV over NT. And R is just a constant, so R should always equal each other. All right, so from there I can write PV over NT equals PV over NT. And if you're looking at that being like, oh my God, I hate people deriving things, I have to put up with it in math and physics, don't make me put up with it in chemistry as well. You can let that pass right through your brain. This is just your emergency, oh my gosh, I can't remember the second equation, how do I get it from the first one? So this is that second equation that we're going to need. And I'm going to put 1's on the left, and I'm going to put 2's on the right. And then what I'm going to tell you is the 1's represent an initial condition. And the 2's represent a final or a second condition. So when we use this PV over NT equals PV over NT, we have some kind of change that's taken place. So let's imagine you have a balloon, it's escaped, it's floating up into the upper atmosphere. Now there's a different temperature, now the volume's different, now the pressure's different. So something had to change. On the other hand, if you look at PV equals nRT, this describes one condition. So let's imagine you've got a basketball and you know the volume, you know the pressure, you know the temperature, and you want to know how many moles are inside. That is where PV equals nRT could come in, because it's only describing that one condition. Where we might use this one down here is if you took that basketball and now you moved it somewhere. Let's say you took it under the water where there's a higher pressure, up to the upper atmosphere where there's a lower pressure, but something had to change. So in this PV over NT equals PV over NT, there must have been some kind of change. So I'm going to say a change occurred. All right, and so we're going to look at these more, and we're going to talk about when to use each equation. But before we do, I want to talk more about that PV over NT equals PV over NT. So those of you who've taken the Chem 2 and you have rigorously learned all these, you may not believe me that PV over NT equals PV over NT will work for any of them. So I want to show you how that works. All right, so here is Boyle's law. I'm going to go ahead and put this in a different color. So what I'm telling you is that instead of using P1V1 equals P2V2, we can use PV over NT equals PV over NT. Let me put in my numbers. All right, so now I want to show you why this equation right here can actually be the same as that big Boyle's law equation. All right, so Boyle's law, in this problem, we have a pressure 1 and a pressure 2. So the pressure has changed. So I'm going to go ahead and put a check mark by the P. We need that pressure because it's changing. Volume, volume 1 and volume 2. Again, we need the volume because it's changing. All right, nowhere in this problem did they discuss the number of moles changing. So because it is not discussed, I'm going to cross it out. So you'll cross it out either if it is not discussed or if you are told it doesn't change. Next up, temperature. This problem doesn't discuss temperature. It probably should because it's going under the water where it is going to be colder, but it doesn't. So I'm going to cross out the T as well. So now let's zoom in here. The only thing we are left with is P1V1 equals P2V2. So you take your PV over NT equals PV over NT, and you cross out anything that's not needed. Then you will be left with the correct formula. So here we were able to find our Boyle's law. But what I'm going to promise you is it will work for any of those laws. Everything except for the ideal gas law. And technically you could make it work for the ideal gas law, but my recommendation is to use the ideal gas law separately. Okay, So again, PV over NT equals PV over NT can be used for anything in this blue box here. And we're going to return to it in a little bit. But let's go ahead and take a look at this problem. So this says using the ideal gas law. And we've got two different conditions here. We have PV equals nRT and PV over NT equals PV over NT. And we're going to figure out which formula is the correct one. So let's take a look at this problem. All right, so we have our calcium carbonate and it's decomposing upon heating to give calcium oxide and CO2. So a sample of that calcium carbonate is decomposed and the carbon dioxide collected in a 250 milliliter flask. All right, so we know our volume. It's 250 milliliters. So I'm going to go ahead and label that as our volume. All right, next up, after the decomposition is complete, the gas has a pressure of 1.3 atm and a temperature of 31 degrees Celsius. So here is our pressure. And over here is our temperature. Of course, we will have to put it into Kelvin. Any gas law, regardless of whether R is in there, you always have to have that temperature in Kelvin. All right, so now we're being asked how many moles. So I'm putting N equals question mark, how many moles of gas were generated? And down at the bottom is that R constant I wanted you to know. So it's fine with me if you know 0.0821 or if you know it to more significant figures, 0.08206. Either one's fine, just know one of those. All right, but before we go on, we've got to decide which of our equations we want. So let's take a look at them. We have PV equals nRT, and we have our PV over NT equals PV over NT. So what we're thinking about is this one condition, or is there something changing about our gas? One good way to figure that out is looking to see if you have two different amounts for a variable. So for instance, let's run back to that Boyle's law. All right, so at Boyle's law, we had a volume 1 and we had a volume 2. So we had two different amounts for volume. And then for pressure, we had pressure 1, and then we were asked about a second pressure. That tells us we have a before and after. That tells us we need PV over NT equals PV over NT. Now let's go back to the problem we're working on. All right, here there's only one pressure, there's only one volume, only one temperature, and it's asking about one value for the moles. So because of that, we cannot use this one over here. So the PV over NT equals PV over NT, that is for a before and after. And you'd have to have two pressures or two volumes or two amounts of moles or two amounts of temperatures. So if you do not have two different values for the same variable, you can't use that one. So since we cannot use that PV over NT equals PV over NT, we are using PV equals nRT. And I know you might be thinking, well, hey, I know we're using PV equals nRT because it says so on the top. That is true, but on a test or quiz, that will not be the case. You won't have a nice little label like that. Okay, so we were just talking about how we're going to use PV equals nRT for this equation. So let's go through this one together. So we're going to use PV equals nRT. All right, the pressure we have is 1.3 atm, right over here. Next up, our volume is 250 milliliters. But we are going to need to convert that into liters because of the values in R here, because of the units of R. So we do need the liters there. So I'm going to convert this. And our conversion factor is for every 1,000 milliliters, we have 1 liter. So it's going to be 0.2500 liters. And I'm keeping those zeros for our significant figures. All right, so next up is N. And we didn't know what N was, so I'm going to put N equals a question mark. We don't know yet. All right, so next up, we have our R value, and that R value, let me get this circle out of our way here. Our R value is 0.0821. And that's liters times ATM over moles times Kelvin. And next up, we're going to need our temperature. So our temperature way back here we said was 31 degrees Celsius, but anytime we're in a gas law, whether or not we're using R, we always have to be in Kelvin. So 31 degrees Celsius plus, we can say 273 or 273.15. With significant figures, that 0.5 really does fall off, but I found most students feel more comfortable just always tacking it on there, and there's nothing wrong with doing that. All right, so 31 plus 273.15. All right, so it looks like 304.15 Kelvin. Although by sig figs it would be 304, but I'm going to go ahead and leave everything because we're in the middle of a problem. All right, so we are plugging into our PV equals nRT. So let me go ahead and write that one more time. PV equals nRT. And now I'm going to start with our pressure. We said pressure 1.3 atm times our volume, and volume in liters 0.2500 liters equals, and I'll put this in a different color, and that is N. So N, we don't know what N is yet, but we're going to find that. R 0.0821 liters times ATM over moles times Kelvin, like so. And finally, our temperature, 304.15 Kelvin. Just write this a little clearer. There we go. All right, so PV equals nRT. So I'm going to divide both sides by 0.0821 liters times ATM over moles times Kelvin. And our temperature. And through the magic of the iPad, I'm going to copy this over. There we go. So dividing it on both sides. And the R's will cancel and the temperatures will cancel. So the number of moles, N, is going to be 1.3 times 0.2500 divided by 0.0821 and also divided by 304.15. So let me go ahead and do that. All right, so 1.3 times 0.25, and I don't need all those zeros in the calculator. They'll divide by 0.0821 times 304.15. Whoops. 304.15. There we go. All right, so let me make this a little bit bigger. So one thing to be careful with when you're dividing, in the denominator, you need those parentheses. If you don't have those parentheses, you're going to get a really unusual answer. All right, so it looks like our number of moles, are 0.0130. I'm actually going to say 0.013, and the reason is I'm looking at smallest number of significant figures, and I see two significant figures right over here in our ATM. There we go. So 2 sig figs in the ATM, so I'm going to end with 2 sig figs. Remember, the zeros out in front don't count as significant figures. So these will be our moles right over here, 0.013. All right, so that's our final answer for this problem. Because here all we were asked to do is find the number of moles. So one more time, just when you approach a gas problem, you want to think about which of the two formulas I have up at the top is a correct one to use. If you have a before and after, it's that formula on the right that I have X'd out. PV over NT equals PV over NT. Another way to think of it is if you have two different values for the same variable. Two pressures, two volumes, two numbers of moles, or two temperatures. That's PV over NT equals PV over NT. In this case, it was a PV equals nRT because we had only one value for each of those variables, pressure, volume, temperature, and then we were asked to find the moles. All right, so next up, this slide is all about R, the R that we know and love. So it is a constant. So you might be looking at this thing saying, well, hey, it's not a constant, it changes. But the only difference here is that it is in different units. So there has been multiple unit conversions here. So for what we're doing right now, you need to know the top one, this one right up here, and that is our 0.08206. And I don't care if you know the 0.0821, that's the one that I use the most, or if you use 0.08206. Either way, I want you to know one of those. Later on, we're going to start using the one below, and that is in joules. Just make a little neater box around this one. All right, so the one in joules later on you will need to know, 8.314. But the rest of them you do not need to memorize. You can always convert either into ATM or into joules. All right, so here is our next one. It says an inflated balloon has a volume of 6 liters at sea level, which we assume to be 1 ATM, and it's allowed to ascend or to rise to an altitude until the pressure is 0.45 ATM. During the ascent, the temperature of the gas falls from 22 degrees Celsius to negative 21 degrees Celsius. And we are going to calculate the volume of the balloon at its final altitude. So first, let's go in and let's mark these with our variables. So this is volume. This is pressure. Here we have more pressure. Here we have temperature. Here we have another temperature, and we're going to be asked to find the volume. All right, so now let's talk about the two formulas we were looking at. We were looking at PV equals nRT, and we looked at PV over NT equals PV over NT. And we've got to decide which one of these equations is the right one. Now remember this equation here on the right, that one is when we have a before and after condition. But you can also tell when you've got two numbers for the same variable, and we have that here. You've got two pressures, you've got two volumes, oops, and you got two temperatures. There's no way you could use PV equals nRT here because you couldn't fit all your numbers in there. So in this case, we do not want the PV equals nRT. Instead, we want that PV over NT equals PV over NT. All right, but before we go on, we've got to decide what we want to keep and what we want to get rid of. All right, so we have pressures listed here. So I'm going to keep my pressure. I also have volumes listed, so I need to keep that volume. I have temperatures, so I'm going to keep that temperature. But we don't know anything about moles. It doesn't tell us the moles are changing. And in fact, they shouldn't change because this isn't a balloon. So it's a sealed container. If we assume that no air escapes, the number of moles should not change. So I'm going to cross out the ends, and I'm going to write what we've got left. And what we have left is PV over T equals PV over T. I'm going to go ahead and put ones on the left and twos on the right. And this is now the equation that we want. PV over T equals PV over T. And just to go back, way back, before you believed me about PV over NT equals PV over NT, there it is. All right, what we have just done is we've just created the combined gas law. PV over T equals PV over T. So by crossing out the number of moles, because we didn't need them, we arrived at that combined gas law. So I'm hoping that everybody is starting to believe me a little bit that if you start off with our new favorite formula here and you cross out anything you don't need, you will arrive at the correct gas law. All right, so let's go ahead and go back. Oops. There we go. Okay, so we decided that it was PV over NT equals PV over NT, again, because there's a before and after, or you could think of it as we had two pressures, two volumes, and two temperatures. Our problem did not mention moles, so we got rid of those moles, and we arrived at the formula that's in the purple box there, and that formula is going to be our combined gas law.